So today we're going to be doing applications of the theory that we've developed, and what we're going to go for first is called the time-dependent heat equation on the line. Okay, so the setting is like this. You have an infinitely long rod. So we immediately step away from reality to this. So there's an infinitely long rod, and the rod has an initial heat distribution. So that heat distribution is described by some function f of x. So this is the initial heat distribution. Okay, and so we want to describe what happens to the heat distribution as time goes on. Okay, so the way we think of this is we introduce a time axis here, and so and we let u of xt denote the this is the heat at position x, at heat at position x, and at time t. Okay. Okay. So time is progressing forward. This is the heat distribution at time 0. What? Okay. I'm not sure what's going on, but oh, you forgot your glasses.
Sorry.
Okay. 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 And it turns out that so physical considerations imply that this thing must satisfy this sort of equation, this sort of partial differential equation. That the partial of u with respect to t is the same thing as the second partial with respect to x. So this is the differential equation, and then our initial condition is that u of x0 is going to be this function f of x, okay, which we'll choose to be a Schwartz-class function. Okay, so so what we do is we we proceed formally. And proceeding formally basically means that we're going to move ahead. We're not going to worry about if things actually work. We're just going to assume that everything we do is legal. Okay. So we take, in particular, we're assuming that u is in the Schwartz-class in x. Okay. We're assuming that u is in the Schwartz-class in x, and so that we can take the Fourier transform in the first variable. Okay. So we take the Fourier transform. In x, right? And so on the left-hand side, we're just taking the Fourier transform in x. So we end up with this, right? This hat is the Fourier transform in the first variable, and then on the other side, right, we're differentiating with respect to x, and so when you take the Fourier transform of the derivative, you get you multiply it by 2 pi I x, so you get the square of that. So you get negative 4 I squared x squared. Sorry, it'll be c squared u hat ct. Right. So this is nice. Our partial differential equation turns into this sort of thing. We lost the partials with respect to x. Okay. So this turns into an ordinary differential equation ordinary differential equation in T, right? So, you know, the derivative over the function is some constant. Okay, and so so that yields that u hat must be of the form e to the negative 4 pi squared 4 pi. Oh, this should be this should be pi squared. Sorry, pi squared, but 4 pi squared c squared t with some constant that depends on c. Okay, so that's what happens to the That's what happens to the partial differential equation, right? And then when we apply the Fourier transform to the initial condition, so the initial condition, when you apply the Fourier transform to it, just turns into u hat c0 equals f hat c. Right, and so that tells you that this a of c must be f hat of c. Right, and so so what do we get? In the end, we get that if everything we did was legal, then we would get that u hat of ct would have to be f hat of c e to the negative 4 pi squared c squared t. Right. So that's what our solution will look like. Okay. In other words, okay. In other words, U is going to look like the convolution. U must be a convolution of f against some other function, where the Fourier transform of that function is e to the negative 4 pi c squared t. Right? Because if this is true, then when we take the Fourier transform of it in the x variable, we should end up with f hat times this thing. Okay. Okay. So a little bit of consideration. So claim h sub t of x is actually going to be the dilated Gaussian, the Gaussian dilated by 4 pi t. Okay, right. And the reason is that, well, if we take the Fourier transform of the dilated Gaussian, right? Dilated Gaussian was dilated by the square root of this, right? And so that turns into the scaling by the reciprocal of the square root, right? I'm sorry. This was dilated by one. Sorry. This was dilated by 1 over 1 over the square root of this, right? Right, and so, right, and so this thing, what this turns into is the scaling by the square root of this. Yeah. So we get 2 square root of pi t c, right? Which is just e to the negative pi, 4 pi t c squared, which is what we want. Okay, so what this says is that if everything we did was actually legal, then the solution would look like solutions could be obtained by convolving them with this kernel. Okay. So that's the model. If everything was legal, then whenever you start out with an initial heat distribution, then you could find a solution to the heat equation by convolving with this kernel. And then solutions could be obtained via convolution with this kernel h sub t. Okay. And this h sub t is called the heat kernel. Okay. So I have to say that I'm not so familiar with this stuff. I'm not very familiar with this stuff, and there's a couple points here where I'm actually not sure. I think there might be some mistake, and I'm not sure. I'll show you when I get to this. Yeah, Jane.
There with the after take Fourier transform in X.
Yeah.
On the left hand side, is that the Fourier transform, the derivative of the Fourier transform, or should that be the Fourier transform of the derivative?
That is the derivative of the Fourier transform. Right. Because when you take the Fourier transform in X, this ddt doesn't get affected by it, right? It's sort of, you can pull it out.
Okay.
You can pull it out. Yeah. Okay. Okay. So, all this suggests that it should be possible, that what we want to try is to convolve our function with the heat kernel to get solutions to the heat equation. Okay, so okay, so here now we'll show that actually does work. So for S, for F in the Schwartz-class, let U of t, Q of xt be F convolved with H sub t at X. Then when U of xt is twice differentiable on the upper half plane, continuously twice differentiable on the upper half plane, and solves the heat equation. Two, U of xt converges to F uniformly in X as t goes to 0. And thus is continuous on the closed upper half plane. And 3, u of xt actually converges to f in L2 as t goes to 0. Okay, so this thing actually does work as a solution. Right? It solves the heat equation and it converges back to the boundary values that we desired. Okay. So the second one we don't need to do. We have that already because it's a Schwartz function convolved with a good kernel, right? And as delta goes, as the dilation factor goes to 0, then we recover our function uniformly. Okay, so what we have to do is prove the first and third part. Okay, and so what we do is we use Fourier inversion. We say, well, look, let's rewrite this thing in terms of the inversion formula. Right, so it's going to be the integral, the inverse Fourier transform of the Fourier transform. Right, so here's the Fourier transform, h hat t c, and we take the inverse Fourier transform of that. Right. And remember that this thing was chosen so that its Fourier transform would be e to the negative 4 pi squared c squared t. Okay. Showing that this thing satisfies the heat equation is just a matter of now differentiating this, right? We want to show that the first derivative of this thing with respect to t is equals to its second derivative with respect to x. And this is a little bit of a cheat, but the Schwartz-class, since f hat is in the Schwartz-class, we can differentiate under the integral. That is, the derivative can pass inside the integral. Yeah.
What property of the Schwartz-class allows you to do this?
So it's actually dominated convergence that allows you to do this.
Because we have the
right, exactly. Yeah. So because of the rapid decay, you can use so-called dominated convergence theorem, and that will allow you to change the order of the limit and the integral. So yeah, so secretly, this is the dominated convergence theorem. Okay. So and you see that differentiating 1 with respect to t is just going to get you a constant of negative pi squared c squared. Differentiating twice with respect to x is going to give you that same constant, right? Because you're going to get 2 pi I c squared, which is the same constant. So you see that the first derivative with respect to t is the same thing as the second derivative with respect to x. Okay. Now, for the second part, is it okay if I erase this? So. Thank you. Okay, for the second part, we want to show that these things, we want to show that, so for this part, we want to show that that we have convergence in L2, right? In other words, that the difference between these guys goes to 0. Okay, and so again we pull out a trick, which is instead of looking at this thing, we're going to look at it on the Fourier transform side. So it's kind of the moral of all of this. Like everything is better on the Fourier transform side. So like you have a problem, just move it over to the Fourier transform side, and maybe it's easier to deal with over there. And in this case, it is. So you say, okay, well let's take the Fourier transform. So by Plancherel, the left-hand side equals the L2 norm of the Fourier transform. So we get you had ct minus f hat xc squared dxc, right? But u hat is just f hat against the Fourier transform of the heat kernel. Right. So if we factor out, right, factoring out the Fourier transform of f, we get this the Fourier transform of the heat kernel, which was that thing e to the negative 4 pi squared c squared t minus 1 quantity squared dx. Right. Right. So at this point, we play. So we want to show that this thing goes to 0. Right. We want to show that this thing goes to 0. Well, we play the same trick that we've played before. We say, well, look, this thing here is in the Schwartz-class, so we can make the integral of this guy as small as we desire. Right. Right. This thing, this is some number, this is smaller than some constant 1. Right? So.
As in, you can make it as small as you want outside of some.
Yeah, outside of some interval. Right. So since f hat is in the Schwartz-class and f hat squared is in the Schwartz-class, we know there exists some constant, there exists some interval, outside of which this thing is smaller than epsilon over 2, say. Right. And then you split this thing into 2 parts, right? You split this thing into 2 parts, and you say, well, on the other part, we've got so then, right? So so this thing is controlled, right? So we split this into 2 parts. This thing is going to be equal to the integral outside plus the integral inside. Right, and then inside as t goes to 0, right? So as t goes to 0, this thing goes uniformly to this also goes uniformly to 0. Right. This thing goes to 0 uniformly, right? And this is bounded, right? is bounded, right? So we can make this we can make this thing, smaller than the bound squared divided by the length of the interval. Epsilon over 4 times the bound squared over the length of the interval, and so we can make this thing. So we can make this thing smaller than epsilon over 2 also. Right? So we've seen this argument I think 3 times now. So maybe we don't need to say it anymore. The usual argument using the Schwartz-class nature of one of the factors. Okay, so that's that. So indeed, it does turn out that getting the solution just involves convolving your boundary, your initial condition against the heat kernel. So that's pretty cool. Okay, yeah.
Maybe I'm just getting confused. What does... Oh, sorry, we're proving... Oh, never mind. I thought we were trying to prove uniform convergence, but we're not. We're just proving L2. I was like, what does it mean to be uniform when x is in our integral? But no, here, this is just proving L2. We had already proven the uniform part.
That's right.
Okay, cool. Thank you.
Yeah. So I think you're probably looking at the corollary, which is the thing that I actually I'm a little confused about it myself, so maybe you guys can help me think about it. Okay. And in fact, I'm not even sure that we need this corollary to get the uniqueness, but in any case, for fixed t, right, we're convolving the boundary condition, which is Schwartz-class, against the heat kernel, which is also Schwartz-class. So each of those things is in the Schwartz-class. Okay. Right. If we fix t, each of those functions for fixed t, u xt for fixed t is in the Schwartz-class. Okay. Yes.
Why is f of x Schwartz-class? Is that...
We just assumed it.
Oh,
yeah,
okay.
Yeah. Yeah. That was part of just part of the assumption. Okay. Now the corollary says the following. Okay. It says that u blank t is in the Schwartz-class actually uniformly in t, in the sense that given any t, given any pop t bigger than 0, if we look at the function and take any derivatives of it, and multiply that by any monomial, so k and l bigger than or equal to 0, for fixed k and l bigger than 0, if we look at the supremum over all x, and also over all t, all little t between 0 and capital T, then that's bounded independent of t. So uniformly in t. Okay. Okay. So okay. In other words, not only are these guys rapidly decreasing in x, but these these bounds, right, the supremum of this thing is going to be finite, independent of t. Okay, so they're uniformly in the Schwartz-class. Okay. Okay, so the proof. So here's the proof, and so we'll do it just for the case where L is equal to 0. Okay. Okay. So let's consider U xt, the size of U xt. Well, we're going to split that into two parts. Okay. Right. This is right, f convolved with h sub t. This is f convolved with h of t x. Right. In other words, the integral of f x minus y h sub t y dy. Okay, so yeah. So what we're going to do is we're going to split it into two parts. So we'll split the integral into two parts, where y is less than or equal to absolute value of x over 2, and outside of that, y is greater than or equal to absolute value of x over 2. Okay. So if we look at the first part, y less than or equal to absolute value of x over 2, f of x minus y, ht y dy. Right. So let's look at the integral of the absolute value, right? F is in the Schwartz-class, right? F is in the Schwartz-class, so we can bound that by some constant over 1 plus x minus y in absolute value to the n. Right. Okay. Right. But on the other hand, y is smaller than the absolute value of x over 2, and so this x minus y, right, is smaller than 3/2 absolute value of x and larger than half of the absolute value of x, right? So we can replace this thing by the absolute value of x, right? So we get that this thing is controlled by we replace that by x and we pull it out of the integral. We get maybe slightly different constant, absolute value of x. Oops. Then the integral of a heat kernel, right? And if we integrate over all of R, then that's just 1. Okay, so we know that this thing is that the integral is going to be smaller than 1. Okay, so that gives us the control we want over this term, where we're integrating over near the origin, right? That's the kind of decay. For any n, this part is smaller than this part is rapidly decreasing. That's good. Okay. Now for the second part, this is the part that I'm suspicious of. So for the second part, okay. So for the second part, you say, well, right, we're looking at f of x minus y kernel for y that's bigger than x over 2, and you say, well, look, the heap kernel is this thing, right? This is is that right? That kind of looks wrong to me, but 1 over 4 pi t root e to the negative we're going to get pi that's going to be, wait, hold on, e to the negative pi x squared over the square root of 4 pi t, right? So we get, oh, that is right. Okay, so e to the negative x squared over 4t, right? E to the negative x squared over 4t. Okay, right? And then you say, well, look, so that all of the sorry, that should be a y. Right, that should be a y. So all of the y's are bigger than x over 2. So we know that that this thing is bounded by e to the x squared over t, basically e to the x squared over t, negative x squared over t times this constant here. Right? So Stein turns all the constants into c's. I'm going to just call them c's. That c is not the same as that c. Okay. Okay. So what happens, right? That we get that this thing in absolute value is controlled by this, independent of y. We can pull it out, right? And we get the integral of sorry. Let's do this. Right. So we're going. We get the integral. We get the integral of f, but that's just some finite number, right? So we get. So we get that this thing is controlled by some other constant, t to the 1/2 e to the negative cx squared over t. Okay. Right. Which is, as you see, it's just it's basically a dilation of the Gaussian. Dilation of the Gaussian by 1 over root t. Right. It's dilation of the Gaussian by 1 over root t. Okay. So this is the part where I'm not really sure what happens. They say the two bounds together give you this gives you that your function is also in the Schwartz-class uniformly with respect to t. Right. The first part that makes sense to me, but then the second part I'm actually a little confused because this bound doesn't look like it's enough, right? Because as t goes to 0, right? So for example, look at when x is equal to 0, right? We get 1 here, and we get a constant over t to the t to the half, right? And as t goes to 0, that becomes infinite, right? So that doesn't even give us a bound on the size of the function, right? That doesn't give us that the function is even that the set of functions is bounded, right? Right. So I'm not sure about this. Anyway, I'll leave it as a question. But in any case, it is true that, so as long as we stay away from 0, right, as long as we stay a fixed distance away from 0, then I think it's okay. So that is, as long as t is within, some, some interval like this, then this will be enough to show that we've got the uniform Schwartz-class. Yeah, and I think that's actually all that we need. That's actually all we need. So yeah, I'll leave that as a question. I look back at my video from years ago when I first taught this course, and I was equally confused at that time. Yeah. Okay. Yeah. I don't think we actually need what they're trying to get. Okay. And the main application in here is to get the uniqueness of the solution. So. Okay. So suppose x dot t satisfies the following. One, partial of u with respect to t equals second partial with respect to x on the upper half plane. 2, u x0 is 0, so it's 0 on the boundary. 3, u is continuous on the closed upper half plane. And 4, u is in the Schwartz-class uniformly. Okay. In whatever sense. Okay. Okay. Then u must be 0 everywhere. Okay, so that is, there's only one solution, right? There's only one solution. If you have a solution and it has the same values on the boundary, then it must be identical everywhere. Okay, right, if you've got two solutions, they satisfy the heat equation, they satisfy these smoothness conditions, and they're equal on the boundary, then they must be equal throughout time. Right? There's only one way that the heat equation evolves. And the proof is kind of fun. It says relies on this idea called energy. So we define the energy at time t as just the L2, the square of the L2 norm. So E of t is going to be the L2 norm of the function squared. In other words, the integral of u of xt squared dx. Okay. So notice that E is always going to be positive, right? It's the integral of something positive, non-negative. And we also see that E at time 0, well, that's just the integral of 0, so there's 0 energy at the beginning. And so what we're going to show is that that the derivative with respect to time is always less than or equal to 0. And so the energy must be 0 throughout. So claim that the derivative of the energy with respect to time is going to be is always going to be non-positive. Right. So that will be enough. Okay. So so consider the derivative. Right. Right, and this thing is of course u times its complex conjugate. Right. So when you differentiate it, right, again we differentiate under the integral sign. We get the partial of u with respect to t times u bar plus u times the partial with respect to t of u bar. Right. Okay. Now we use the fact that we have the heat equation, right? So that u satisfies the heat equation. So we say, okay, now this is going to be dx squared u dot times u bar plus u times dx squared u bar. Dx. Okay. Right. So at this point, we use integration by parts to shift one of the derivatives onto the other term. Okay. So that will give us because these things vanish at infinity, we just get negative of the one with the shifted derivative. So we get dxu, dx u bar dx, right? But that's the same thing as -2 of dxu xt dx. So that's negative, not positive. Okay. So it's at this point that that Stein and Schwartz say that we need to use the uniformity. So this is one thing I admit being a little confused by. They say it's at this point that we need the uniformity of these guys, that these guys are uniformly in the Schwartz-class. And
but D isn't varying here.
sorry. Yeah, the thing is that T, right? T is a constant at this point, right? T is a constant at this point. So why do you need anything involving uniformity of T, right? T is constant at this point. All these guys are in the Schwartz-class, so we can just use, they vanish at infinity, so it should be okay. And it's not clear to me why they want uniformity at all. Further, why you would need it from 0 to t is also mysterious, because you're taking a derivative, which is just a local thing, right? You just need it near your t, right? You need it in a small interval around your t, if at all. And it's not clear that you need it at all. So, yeah. So I have to say I'm kind of a little confused about what's going on here. Maybe it's just a mistake on their part. I think I want to ask somebody who actually does this sort of thing. Ah, my gun! Is it already this time? Okay, class is over. Okay, actually that is actually a good point to end on a point of confusion at 11:50.